Hey everybody, so in the second video now, this is the second video in the series, I'm going to explain the physics in some detail, but not all the way. You will be required to figure out how to apply this to the windmill on your own, but I will walk you through the physics again as a kind of a refresher from what we've done in the past. So Newton had three laws. He said an object at rest stays at rest, and an object in motion stays in motion at the same velocity until it's acted on by an unbalanced force. He also said that the force acting on an object is equal to its mass times its acceleration, or F equals ma. And his third law said that for every force, there's an equal and opposite reaction force. And we went over these in a lot of detail in the beginning of the year. Think about how each of these laws is going to affect a windmill. Newton's first law says an object at rest stays at rest and an object in motion stays in motion. So what does that mean for my windmill? Is my windmill normally at rest or is it in motion? What do I need to do in order to make it move? Well, according to his first law, I need to add an unbalanced force. So where is that force? Where is that energy going to come from? Answer those questions for me, and you've applied Newton's first law to a windmill. Now, I want to be clear. Please do this in your own creative way. I'm not looking for you to just answer these four questions on one slide. I'd like you to talk about how does this law apply to the windmill? What is the unbalanced force? How is it going to act on it? I don't want you to just say, is it at rest or in motion? It's at rest or it's in motion. Like, I don't want you to just answer these questions. I want you to do it in a paragraph. Newton's second law says that force equals mass times acceleration. Well, that's abstract from a windmill. That's just an equation. I want to add it to my windmill. So how do I do that? How do I get F equals ma to add to my windmill? I have to name and identify those forces. So where does the force in this equation come from? Well, that's the wind blowing on the windmill, right? The wind is going to provide the force. And that's going to equal the value of that force in newtons is going to equal the mass of the windmill blades, the mass of the object that's moving, times the acceleration in meters per second squared. So if I know the force of the wind and I know the mass of the windmill, then I can figure out what the acceleration of that windmill should be. Now, it's easy to measure the strength of the wind. We can do it with a tiny instrument. You put it up in the air, and you can measure the strength of the wind. And I know the mass of the windmill. I know that because I know what I'm building it out of. I know how big it is, so I can come up with the mass, which means the acceleration is what I'm going to be measuring. It's what I'm interested in getting. I want the acceleration piece. So where does that come from? That's how fast the windmill turns. And since the speed it turns at becomes the energy it produces, it means that the more I can get it to spin, the more energy I'm going to produce from it. So F equals ma is the same as the force of the wind is equal to the mass of the windmill blades times the energy produced. Or if what I'm really looking for here is the acceleration, then that's going to equal the force of the wind divided by the mass of the windmill blades. Now, that may be a lot of information all at once, but all I've really done here is I've taken this equation and made it real terms. Instead of saying F equals ma, I've just said the force of the wind is equal to the mass of the windmill blade times the acceleration that it's undergoing. Okay? So let's try it with numbers, because that can make it a little more clear sometimes. If we say, for instance, here in a normal setting, the force of the wind is 10 newtons, and the mass of the windmill blades is 2 kilograms, well, then I know that the acceleration is going to be 5 meters per second, or meters per second squared. So that's just a normal flat line. We're just assuming that's the strength of the wind and that's the weight of the windmills. I made these numbers up. If I could somehow, if I could somehow harness the wind in more strength and get more of the wind, that would go up to 20 newtons. Let's say I could somehow make my windmill bigger and I could catch more of the wind. Now there's more wind force pushing on my windmill. And if the mass has stayed the same somehow, that would double my acceleration. So when I increase the force, if I keep the mass the same, I increase the acceleration. So if I could find a way to make my windmill gather more air, more wind energy, without increasing its mass, or by increasing it just a little bit, that would let me gain more acceleration. Things like the end of the blade or the thickness of the wing, right? Those sorts of things can change the amount of air I capture without changing the mass of the wing too much. And some of those 3M materials that they ask you to add at the end, some of those can apply more they can catch more of the wind without increasing the mass too much. And then that would increase the acceleration a lot, right? But if I increase the mass of the blades and it doesn't capture any more of the wind, that reduces my acceleration. So now I've gone from, oops, that's unfortunate. Now I've gone from 10 newtons of wind power, just like the normal setting, but I've increased the mass of these windmill blades to 4. They were 2. I've doubled them. Well, that reduces my acceleration from 5 to 2.5. So now my acceleration is going down as the windmill blades get heavier. Now, the tricky part of this is that when I increase the mass of my windmill blade, I'm probably also increasing the amount of force acting on it. So what I'm getting is a value in between these two settings where the mass has gone up, but so has the force of the wind. And how is that going to affect my acceleration? It's a balancing act. How much is too much and how much isn't enough, and finding just the right shape and size. If I rotate the blade a little bit, maybe that will make it capture more air. If I can make the end of it wider, maybe that'll catch more, but maybe that adds too much mass. Maybe I can reduce the mass by making it narrow and not lose too much of the wind that it would capture. All of these are variables you have to look at. So, of the 3 variables, the mass of the blade is the easiest for me to change. If I increase the mass or the size of the blade, does the acceleration go up or down? Does the force of the wind go up or down? If I could somehow increase the force of the wind, does that change the mass of the blade? Does the acceleration change if I increase the force of the wind? And if it does change, does it go up or does it go down? Are there ways to increase the size of the blade without increasing its mass? Think of the 6 variables we can manipulate in our construction in the next video. Which ones might increase the size without increasing the mass? And then the third law. For every force, there's an equal and opposite reaction force. What is the action force that causes the windmill to turn? And what is the reaction force that pairs with this force? Remember, it hurts to punch a wall because when you punch the wall, you apply a force to the wall and the wall applies a force back to your hand. So if that's true, how does that action-reaction force pair apply to the windmill? Tell me about that. Those are Newton's 3 laws. Now, admittedly, a lot of it is the second law. But if you can tell me how these 3 laws will affect a windmill, then you've done it. All right, that's going to master that standard, and it's going to finish you off as your final, as your midterm grade for that standard, that DCI about forces and physics. Okay. Now, stay tuned for the next video. And you can watch that one if you need a little refresher on our next step in this process, talking about energy transfer.